Right, so here's a quick summary of what we talked about today, just so you know where we're picking up on Wednesday. So we started talking about some of the session 3 problems, which is about base conversion, uh, going from like base 2 to base 3 to base 5, and we didn't get to today, but modular arithmetic is coming up. So in session 1, we noticed that remainders play a key role in the repetition or termination of a decimal. After a long division, if the remainder was 0, the division was finished and the decimal terminated. If the remainder was the same number as any previous remainder, then the pattern would repeat from that point, leading to a repeating decimal. So we looked at decimal expansions of 41sts, found some interesting patterns. One thing we noticed was that you could add 141st to 141st and get the digits to 241sts without having to do the long division again. You could do the same thing to get from 231st to 241st to 3 over 41, and so on. And then another thing that we looked at was we saw that the pattern, if you multiply 141st by 10, that gets you, it moves all the place values over by 1, and you get to the next one in the sequence. If you multiply that by 10, you get 141sts, but when you take out 41 twice from that, you're left with 18, because 41 plus 41 plus 18 equals 100. And so you can see that the place value from 10 41sts times 10 moves to 18 41sts. If you multiply it by 10 again, it gets you to 16 41sts. And if you multiply it by 10 one more time, it gets you to 37 41sts. And then that will loop back again to 141st. So interesting to multiply the number by powers of 10. There were 8 different cycles of 5 digits each for the 40 different fractions between 1 over 41 to 40 over 41. Then we looked at the long division expansion of 1 over 142,857. Donna noticed that 1/7 was equal to that decimal expansion, and so it would make sense that the decimal would become 0.00007 repeating. Isaiah noticed that if you wrote that fraction as in scientific notation, you would have 1.42857 times 10 to the negative 6th power. And so again, suggesting how you could get from the fraction to the repeating decimal. Then we looked at writing decimal expansions in different bases, so base 2 and base 3. For example, we can't write 3 in base 2, so 3 in base 2 is 1, 1. And so to turn 1/3 into a decimal in base 2, we would have to do the long division of 1 over 1, 1. And that would look something like this. So 1 divided by 1, 1. Let's give us some decimals. Goes in 0 times. Goes in 0 times. 3 goes into 4 one time. If we subtract, we'll get 1. Oh, now we're back where we started. So we know that in base 2, 1/3 is going to be 0.01 repeating. Let's do one more example of that. So if we look at 1/7 in base 3, for example, 7 in base 3 is equal to 2, 1. And so 1/7 in base 10 is the same thing as 1 over 2, 1 in base 3, which means the long division will look like this. 0, 0, 0. Goes in 0 times, goes in 0 times. 7 goes into 9 once. Subtract, you'll get 2. Goes in 0 times. Let's add some more decimal places, bring down. That's 18, so 7 goes in 2 times. 2. Is that right? 9. 9 plus 6 is 15. That should be a 1. 16. Subtract. We essentially have 18 minus 14, so that should be 4, which in base 3 is 1, 1. Bring down the 0. So now we've got a 9 plus a 3, so that's 12. 7 goes in once. Um, 12 minus 7 is 5, so that's this. And now we've got 9 plus 6, 15. Goes in twice again. And we said that would be 1, 2, 1. Oops. That would actually be 1, 1, 0. Subtract. And now we're back where we started, which suggests that 1/7 in base 3 is 0, 1, 0, 2, 1, 2, repeating base 3. So let's look back at a bunch of patterns. Here we've got 1/3, 1/4, and 1/7 in bases 2 through 17, selected bases. So take a moment, look at some patterns here. Notice which fractions terminate in which bases. One thing that we realized was just like in base 10, because that's 2 times 5, only fractions that are out of powers of 2 and or powers of 5 will terminate. In base 3, only fractions with powers of 3 terminate. In base 4, only fractions with powers of 2 terminate. In base 5, only fractions with powers of 5 terminate. And so we also noticed that 1/7 in base 3 and base 5, the digits in the repeating decimal, the first and the fourth digit pair up to make 3 or 5. The second and the fourth digit pair up to make 5 or 3 or 5. And the third and the sixth digit pair up to make 2 or 5. And then similarly in base 10, you can make pairs of digits that add up to 9. And in base 17, pairs of digits that add up to 16. This is where we left off. We'll continue again on Wednesday on problem 6, but if you'd like, take a look at some of these problems. If you have questions, email me, and I hope to see you on Wednesday.